Hi, this is Dr. Habib once again. I have recently received a lot of requests on the breakdown simulation of p-n junction diodes and metal oxide semiconductor field effect transistors. So the good news is that I have worked on that, and today I am going to show you how to perform the breakdown simulation of diodes and MOSFETs. So let me run the Silvaco TCAD program. And first we will perform the breakdown simulation of a p-n junction diode. So I have already written the code. What I'm gonna do is, first I will build this structure which is entirely silicon based. Our structure is from 0 to 1 micrometer in the x direction and from 0 to 15 micrometers in the y direction. And then initially I introduced p-type doping of the level of 10 to the power of 17 per centimeter cube for the entire structure, and then later I introduced an n-type doping of 1 into 10 to the power of 19 per centimeter cube in from 0 to 5 micrometers in the y direction. And later I performed the breakdown simulation of this silicon based p-n junction diode. So as you already know, we write the command of go atlas, and then we introduce meshing. Meshing is critical. And as you know that we would like to introduce denser meshing around here at the p-n junction at the interface, and less dense meshing away from the junction. So in x direction from 0 to 1 micrometers I have introduced a spacing of 1, while in y direction at a location of 0 I'm introducing a spacing of 1, but then in y direction at a location of 5 micrometers we have the interface over here at 5 micrometers. We have the p-n junction. So we would love to introduce a finer meshing over here with a spacing of 0.005 micrometers. And then away from the junction at 15 micrometers we don't really need fine meshing. So over here I have introduced a spacing of 2 micrometers. Then we define the region. Region number 1, silicon. The entire structure is based on silicon material. I introduced a top electrode of cathode and the bottom electrode is anode over here. As you can see in this structure, the top electrode is cathode because we have n-type material at the top. So we call this electrode as cathode, and we call the bottom electrode as anode because the bottom layer is p-type. Then, as I already mentioned, that initially I introduced a uniform doping of 10 to the power of 17 per centimeter cube for the entire structure and this is p-type doping. And then I introduced n-type doping with carrier concentration of 1 into 10 to the power of 19 per centimeter cube from 0 to 5 micrometers in the y direction, as you can see in the doping profiles over here. And I'm going to run the simulation so you can see it in detail later. Then we introduce models to solve different equations of physics at all the nodes that we introduce inside our structure. Our models are Shockley-Red-Hall recombination, concentration dependent mobility, band gap narrowing, OJ recombination, and field dependent mobility. And a crucial model that we need to introduce over here is impact ionization. But in Silvaco TCAD you cannot introduce it with models. We have to introduce it with impact. The model is impact, And furthermore, there are so many different models in impact. We have Silvaco model, and we have Crowell model, and there are other models as well. But today I have included Silvaco model for the breakdown simulation of a p-n junction diode. And I'm going to do the same for metal oxide semiconductor field effect transistor as well. And then, as you know, that we need to introduce a method for numerical simulation of our structure, and our method is Newton. Solve initial is actually introduced in order to have an initial guess on various parameters of the p-n diode structure under thermal equilibrium. Output actually shows different parameters for the structure, and then band.temp is a really useful command in order to look at so many different parameters: conduction energy level, valence energy level, quasi-Fermi level, recombination rates, doping concentrations, the band gap, and so many other different parameters. And then we save the structure and plot the structure. Later, excuse me, it's really simple and straightforward to introduce the code for the simulation of the breakdown for the p-n junction diode. What we do is, instead of defining a voltage range, we introduce curve tracing for current across the structure. So for example, here we say that we apply voltage to cathode, and we keep tracking the current until our current arrives at a maximum value of 1 into 10 to the power of minus 4 amps under reverse bias. And initially we introduce a voltage step of 0.01, and we keep increasing this voltage step by 1.02 times. So like for example, our initial voltage would be 0.01 volts, and then the next step would be 0.01 times 1.02, and then we keep multiplying each subsequent step with 1.02. So it's going to keep solving the structure until we arrive at a maximum cathode current of 1 into 10 to the power of minus 4 amperes. And then we log the output, we output the log file, we solve the curve trace, and we plot it. And that's it. That is going to perform the breakdown simulation of p-n junction diode. Now let us run the program. Here we see the structure. The material is silicon. So what I'm going to do is I will display the contacts. Here we have cathode, at the bottom we have anode, and I also want to look at the doping concentrations, absolute net doping over here. We click apply and then OK. So here is our p-type layer with the carrier concentration of 10 to the power of 17 per centimeter cube. By the way, if we look at this color chart, we see 17, 17.2 and so on, but it is actually 10 to the power of 17, 10 to the power of 18, 19, and we can also change it to 10 to the powers in settings. That is really simple and straightforward. So then in the structure we can look at different parameters by clicking on tools, then cut line, then introducing a cut line across the interface. So here initially it shows the doping concentrations, absolute net doping. It is 10 to the power of 19 per centimeter cube in this red layer, the n-type layer, and it is 1 into 10 to the power of 17 per centimeter cube in the purple layer. We can also look at some other parameters, like for example we can look at the energy band diagram, conduction, valence energy level, and the quasi-Fermi levels as well. So here is our energy band diagram under thermal equilibrium, and we can also look at the energy band diagram under the application of the reverse bias voltage. So our breakdown, we have also simulated the breakdown IV characteristics for this structure. Let me go to the right settings for this curve. Cathode voltage, so I wanna plot cathode current instead of anode current. We hit apply. Excuse me. So now we can see the breakdown characteristics of this PN junction diode, which is based on silicon material under reverse bias. We see that the current starts drastically increasing if we zoom in on this point around 15 volts. So 15 volts is the breakdown voltage for this silicon based PN junction diode structure. So this is how we simulate the breakdown the breakdown performance for silicon based PN junction diode. Simple and straightforward. And now I will show you how to perform the breakdown simulation of a MOSFET as well. So I'm going to open another file. Let me make sure I have opened the right file. Apparently it is the right file. I have already shown how to simulate the structure of this MOSFET. So I have posted another video, and the name of that video is Silvaco TCAD tutorial on MOSFET based on Athena and Atlas. So if you are in this today's video, I'm not going to go into the nitty-gritty of the structure, and I'm not going to go through each and every line for understanding how to build the structure, because I've already posted another video on that. I will just skim through the code, and then I'm going to focus mainly on the breakdown simulation part for the metal oxide semiconductor field effect transistor. But I can show you some already saved pictures for the structure. So here is our structure. We have the gate over here, and then here is the silicon substrate. We have the aluminum metal contacts for the source and for the drain. Here is the meshing. We introduced denser meshing in crucial regions. Here is the doping profile across the structure. So we have the drain region over here, the source region over here, and then we have separate contacts for the drain region and for the source region. Here is the polysilicon region, and then here is the bulk of the metal oxide semiconductor field effect transistor. So initially over here I have introduced the command go Athena because I have formed this structure in Athena. Athena is a module of Silvaco TCAD in which we can simulate different semiconductor processes, for example deposition, ion implantation, etching, oxidation, and annealing, etc. So I first introduced the meshing. As I already told you that I have discussed the formation of the structure in detail in another video, so I'm not going to focus on the details over here. So initially I introduced the meshing, and then I initialized a silicon substrate, then we performed oxidation, then etching, then oxidation once again in order to form the gate for the MOSFET structure, the silicon dioxide gate oxide. Then we deposited the polysilicon contact for the gate, performed etching in some region, then oxidation once again, then ion implantation for the source and for the drain regions. In fact, for the source region initially, then some more oxidation, deposition of the aluminum, and then we etch aluminum in the undesired regions, and then I mirrored the structure to the right so that we can have the drain side region as well. And then we labeled different electrodes, the gate, the source, the drain, and the substrate, and then we saved the structure. After that, we introduced interface states, and because there is oxide deposited on silicon, and then polysilicon is deposited on top of the gate oxide. This introduces interface states, so we have to account for that. We introduced different models, as already discussed, and impact cell is the model used for performing the breakdown simulation of this structure. I have adopted Newton method for the simulation of the structure, solve initial for initial guess under thermal equilibrium for some parameters of the structure, and I have fixed the gate voltage for this structure to 1 volt, and then I am going to perform curve tracing once again, and in this case our contact is drain. So what the program does is it starts at 0.1 volt, applies that voltage to the drain, and starts measuring the current. And then the next step is 1.2 times 0.1 volt, and then it measures the current once again at that point. And then it keeps increasing the voltage by 1.2 times each and every subsequent step, and keeps measuring the current until the current arrives at 1 into 10 to the power of minus 1 amps, or 0.1 amps. And when it arrives at that point, the program is going to stop performing the simulation. We output the log file, we solve the curve trace, and then we plot the IV characteristics, the breakdown IV characteristics for this MOSFET structure. So now I'm going to run the program. Here is our structure. Once again, we can display meshing. We can display the doping profiles across the structure. We can display the source, gate, drain, and the substrate contacts as well. But we have already done that in another video, so I'm not going to focus on that. Now, let us see the progress of the program so far in the runtime output window. It's simulating right now. It's 4.75 volts. It's increasing the voltage, running the voltage sweep, increasing the voltage by 1.2 times with each subsequent step until our current arrives at 0.1 amps, which we have set in the program. So alright, we are here. We just have to display the right parameters. We want to look at drain current versus drain voltage. So hit apply, and here is our breakdown IV characteristic for this metal oxide semiconductor field effect transistor. So we can see over here that the breakdown occurs around here if I zoom in on that point, and for zooming in, what I'm doing is that I'm holding the left click and making a rectangle around this area, around the knee of the IV characteristic, and then just releasing the key. And now we see that the breakdown actually occurs. Let me go back once again. Yeah, the breakdown actually occurs around 7.2 volts for this this metal oxide semiconductor field effect transistor. So that concludes the session for today. I hope it was informative for you, and I guess that's it. So please follow me for more exciting such videos related to Silvaco TCAD and other nanotechnology related stuff in the future. Take care, and I will see you next time.